Hello everyone, I'm Ashwin, a BTech 4th year student. I'm going to be presenting a demo for my project Talktile. It's an application that helps visually impaired student study. The currently available solution in the market do not convey visual information. On top of that, the solution that are currently available have screen-based gestures. We are trying to improve on that by voice command, making the complete application be navigable by only voice command. And on top of that, we also convey visual information, for example map. So this is it. This is the solution that we are trying to convey. The key feature of our application is our complete application is can be navigated via voice commands, and we convey visual information, for example maps. In traditional setting, for example, a visually impaired student, let's say he is a standard 6 student, for example, he would need separate map, one for soil pattern of India, second map for weather pattern of India, third map for cities of India, and a visually impaired student would have to carry all these three maps. Most of the time, tactile graphics are very expensive to be printed, and multiple schools share them. So for a student studying at home, it is very difficult for him to carry three maps, and they are very bulky also. They are very expensive, they are very bulky. We are trying to solve this problem. What we are trying to do is we are trying to create a system that works with a single map only, a single map of India with states highlighted in tactile, and then with states highlighted in tactile, and then you don't need multiple tactile graphical maps. You don't need multiple maps. With one map only, we digitally overlay multiple maps. For example, the example that I gave before, soil pattern of India, weather pattern of India, and cities of India, all these three maps can be digitally overlaid on top of a single map, so it saves space, it saves money for a student, and they can study at home. So first this, and second, if let's say a student is studying at class 6 standard and chapter, let's say contemporary India, and is in chapter number 1, uh, for moving from page 1 to page 10, you'd have to swipe 10 times to switch between pages. So we are trying to solve this via voice command only, so that via voice command only he can straight away say that go to page number 8, and he moves and the pages like flip, rather than swiping 8 times. So this decrease the cognitive load and increase the navigation speed of the user. So these are a key feature of our application. Impact, we are trying to create a navigation system that is faster, lower cognitive load, and make text more understandable for visually impaired students. So Talktile 4, this is the our app architecture of Talktile 4. So this is the app architecture of Talktile 4. So input media, there's audio feedback, there's camera, and there's processor. So Android device, we have three things. There is camera, there's processor, and there's audio feedback. Once a camera is rolling, camera is placed on top of a map. So let's see the current application, how our application Talktile 5 works right now. So this is the home page that is visible on the screen. This is the home page that is visible, and the volume down button initiates the voice command. And when voice command is initiated, the user says book number this and page number that. For the current example, we are using book Contemporary India and chapter Resources and Development. So for this example, the user would say go to book Contemporary India and chapter Resources and Development. It automatically opens page number 1 of that book. So let's see. So this opens page number 1 of that book. So on the lower half of the screen, we have provided icons for helping visually impaired student. If suppose there is a guardian around or a teacher around, so lower half of the screen contains icon. On the upper half of the screen, we have several gestures that are currently standard for different applications. These are already in the market. Different applications already use these gestures, and on top of that, you can initiate voice command by pressing the volume down button, and when you do that, you can tell app to pretty much do anything. So suppose I want to move to paragraph number 3 from paragraph number 1, and say on page 1 I would say go to paragraph number 3. It will automatically move the cursor to paragraph number 3 and start reading from there onwards. If I want to switch to, let's say, page number 3, I would say go to page number 3. It would move to page number 3 and start reading from paragraph number 1. So this is exactly what we'll do now. So as you can see, it's reading, and when we say go to page number 3, it goes to page number 3 and start reading from paragraph number 1. On that page also, you can move back and forth between paragraphs, you can move back and forth between lines, you can move back and forth between pages. One more additional feature that we added is where am I. The application answers where exactly you are, chapter number, page number, chapter number, page number, and then paragraph and line. So it is for keep it is so that the user know the context, like which line is he or she on. Now this is so that the user understand which line and where exactly in the book he or she is on. So as you can see, this page does not contain any map. Since this page does not contain any map, the feature open map does not work here. If the page contains a map, the app automatically says, before as soon as you open the page, the first thing the app says is this page contains an app. So visually impaired student knows that this page contains an app. So let's say in this particular chapter, resource and development, page 8 contains a map of soil pattern of India. So I'll show you. So right now, if we say go to page number 8, it will move to page number 8. Then as you can see, this page contains an app. So the app immediately say this page contains a map. So the app immediately says that a map is present on this page. Then you say open map, it opens the map screen. So right now, we are not displaying a tactile map on this page, but this is how you navigate to a map, and that this is how you navigate around the application. So this is what a system looks like when you need a map. Suppose you are not using a map, you'd keep your phone as you normally do in front of a mouse, in front of near a ear, or use earphone, however you want. It would be placed on a bench before you for a student, let's say is working in school. But if you want to use map, we have created a special stand like this. So this is a dismantled stand. You have to assemble it, and the stand becomes like this. So the pasted map right now is a tactile map of India. It has all the states highlighted, and you place your phone on top of the stand such that the phone is parallel to the map. As long as the phone is parallel to the map, the app will work correctly no matter the height, and the map should be completely visible on the screen. Like the complete region of the map should be visible on the in the camera frame. So let's see how the map architecture work right now. Map screen architecture work right now. So let's see how map architecture work right now. So we are using the camera. The camera records whatever is displayed, whatever is in front of the camera. So right now, as you can see, it's map. Let's see how does the map architecture work. The map is placed in front of the camera such that the map is parallel to the phone. And when we are processing right now in our application, we are processing we are processing at the rate of 5 fps, like 5 frames per second, to reduce the load on the processor and to reduce the latency. So yeah, the camera X module delivers the live video, and then we filter out every fifth frame, and then we process it. So for processing the frame, we have to pre-process it, and we convert the standard YUV raw image that the camera X module gives us to a RGB image. Then we have to resize it to a 640 by 640. 640 by 640 size, 640 by 640 pixel image. We have to do this because the model that we are currently using for classification is a YOLO V8 model, and that model we have trained on a 640 by 640 pixel images. So we have to resize each image. So then we resize the image, and then we resize the image, and we feed it to the model. So the model that we are currently using, I've said before also, it's a YOLO V8 model. It was a medium size model. So we tried to optimize the number of parameters also, but reduce the training time also. So we trained a YOLO V8 model and deployed it on an Android device in the TensorFlow format, TensorFlow 16 int to be exact. So then the YOLO model outputs the YOLO model output gives us the YOLO model output gives us three things. First is the map region, the region in which the map is present. Suppose the camera frame contains sidebars, let's say top and bottom bar. This top and bottom brown region is waste for us. We do not require it and we do not need to process it. So the YOLO model classifies the strictly the map region for us. And secondly, it gives us the index finger mapping, and along with that it gives us the mapping of the back of palm region of your hand. So this gives us three region, and we need two region for calculating where your finger is present in the map: the finger region and the map region. First, we crop the output of the image. So let's say the image that we fed to the model was a 640 by 640 image, and we the model for the map region only, the model will give us four coordinates: x1 y1, x2 y2, x3 y3, and x4 y4. We would crop the 640 by 640 pixel images according to these four areas, these four classification coordinates, and then we'd have to map the finger according to that. Map the finger bounding box according to this bounding box that we have classified for the map region. This is what we do: adjust finger region according to the map region, then identify the map region from the JSON. Now comes the second part of the application. So how are we digitally displaying, let's say, soil pattern of India, weather pattern of India, or any other map of India in our application? Is We have hard coded the bounding boxes. So let's say Madhya Pradesh, Uttar Pradesh are black soil regions. So we have hard coded the bounding box for our 640 by 640 standard pixeled images, and then for the cropped images, when we know where the bounding box of the finger lie in the outputted images, we know where the bounding box of the finger lies. We check whether the finger lies in that bounding box of the JSON file that we have hard coded or not. If it is there in the bounding box, we speak out the class name. Let's say it's black soil pattern, then we speak out, this is black soil. So the user know that Uttar Pradesh and Madhya Pradesh has black soil. How do we classify whether the finger bounding box is inside the bounding box of the JSON file that we have hard coded? So we do that by if let's suppose there is a if let's suppose there is a region, let's say this green region, and there is a dot inside. Let's say my arrow is a dot. How do we classify whether this dot is inside the green region or not? We would create an infinite array going to the infinity, and if this ray crosses the bounding box region once, that odd number of times, then this means that the point is inside the bounding box. If it crossed even number of times, then this means the point was outside the bounding box. So that's how we classify whether the finger bounding box region is inside the finger bounding box is inside the region bounding box, or the finger bounding box is inside the or outside the region bounding box. Region bounding box here is the bounding box of the, let's say, soil pattern of India. So it's a region that classifies that this is the black soil. So then we know that let's say my finger is in the region of alluvial soil. So we know that this is alluvial soil. We give it to TCS. This is standard Android Studio library. So whatever the region is classified, if it is, let's say it is classified alluvial, so we speak aloud alluvial soil. We give it to text to speech standard library and speaks aloud alluvial soil. One more thing that we have to keep in mind. Let's suppose you keep your finger constantly in the region of alluvial soil. It should not constantly speak alluvial. You would not want that from your application. So we have to check whether the current classified bounding box is separate from the bounding box that was classified before it. That we have to keep. For that we are using a memory variable right now. So we see that variable is different from the current classified bounding box. If yes, then we speak aloud. If no, then we do not speak aloud, since you do not want alluvial to spam you with this word. If the bounding box changes, then we speak out. If the bounding box does not change, then we don't speak out. Now next part come is how are we recognizing hand gesture. One, we are when the camera is on, when the camera is on the stand, upon the stand, user cannot use voice commands properly, because the camera is away, the mic of the phone is away from the user if he or she does not have a earphones. So for that, we have also created one more thing, that is initiating voice command. So the next part of our application is how do the user interact with the application when the phone is up on the stand. If the phone is up on the stand, the user cannot press the volume down button properly, because we have to keep in mind that the user is visually impaired. So for that, we have included hand gestures also. And for recognizing hand gesture, we are using media pipe, since it is very efficient at doing that. So before I told you that YOLO classifies three regions. The first one is the map region, the second one is the finger region, and the third one is the palm region. So the map and finger region are used in classifying which bounding box does my finger lies in. The third region that we have classified is the palm region. That's what we are using in classifying whether the user is trying to make a hand gesture or not. So we cannot to reduce the latency, we have to keep in mind that we cannot process every frame through two ML models. MediaPipe and YOLO V11, like we have implemented in TF Lite, but we cannot process our model through every frame through two ML models. This would increase the latency. So we have to keep in mind which frames do I want to process, and which frames I do not want to process. For that we are right now we are using the palm region. If the palm is present in the frame, then we give that particular frame to media pipe. If palm is not present in that frame, then we do not hand that frame to media pipe, we directly process it. We like skip this layer of processing. If that frame is present, let's say the palm region is identified in the frame, then we give this to media pipe, and media pipe recognizes the gesture. Right now we have implemented only one gesture, rolling your finger backwards like this. But in future this can be used to implement multiple gestures. So this, and then that initiates the voice command, and you can navigate through the entire application via voice command. So this is the architecture of our application. Let's see how does the map region works. So this is our stand. So as you can see, the at least entire map of India should be present in the frame. Otherwise, the app would not. Otherwise, the YOLO would crop out. Like the cropped out part would create difficulty for the YOLO to identify the region. So we should try to keep the entire map in the frame. So whichever region I put my finger in, it identifies it. So as I've told you what the application is right now doing, it identifies the fingertip region, it identifies the map region, it crops the map region from the entire frame, and it maps the finger region according to the map region, and then processes the frame. If the palm region is present, like in this, the palm region is not completely present, so the confidence score of the palm region would be low in this frame. In this scenario, the frame would not be given to media pipe. But if we'll see in the future, the palm would move in the middle of the frame. That would increase the confidence score of the YOLO model. So if the confidence score is high for the YOLO model, then it would be classified as yes. The palm region would be classified as yes, and that frame would be given for processing to media pipe. So this reduce our computing requirements. So as you can see, this is the demo. You can see here that so here you can see. So in the frames before this, the palm region was not completely present in the frame and it was cut out from the frame. So what that does is it was not completely between the map. So what that does is the YOLO model, the confidence score for the palm region for the of the YOLO model is very low, so it does not classify it as yes, and that frame does not go to media pipe. But this frame, since these frames, multiple frames must have gone to media pipe. So these frames, in these frames, the palm region was present in between the frames. So this increased the confidence score, and that frame was sent to media pipe for processing it. So we are using this model. We can correct this model also. Instead of using back of palm now, instead of using back palm, we can use the front of the palm. Since if we can use this part of the hand rather than this part, that would be much better at reducing frame. Even in this, a lot of frames are out of redundant frame are being sent to media pipe. But in future works, we can switch from back of the hand to the front of the hand for better performance. This would reduce redundant frame from being sent to media pipe. So then you can do whatever you want. The application is entirely navigable via voice command. So this was our application Talktile 5. We are actively trying to improve our application further. Thank you.